Today on How It's Made. Pre-inked stamps, guaranteed to leave a lasting impression. Cranberries, more than a turkey sidekick. Putting a high-tech spin on cotton yarn. And road signs, reflective directives. Paid, rush, approved are some of the terms routinely stamped onto documents. Professionals such as engineers have their official stamps too. For years, you had to dab the stamp on an ink pad for each impression. Nowadays, you can get stamps with the ink built right in. The process begins with a design that either the stamp company or its customer creates with standard graphics software. They print the stamp design onto paper using a high-quality laser printer, then place the printout under an imaging camera. They feed in a blank sheet of negative film. Then photograph the printout. 30 seconds later, out comes the negative. The design is light, the background dark. Now they can begin making the mold for the stamp. They apply the negative to a plate of light-sensitive polymer, a plastic-like material. Then they vacuum out the air to prevent defects in the mold. Then they expose the polymer plate to ultraviolet light for approximately 3 minutes. The UV penetrates through the light part of the negative, the stamp design, and hardens the polymer underneath. The rest of the polymer is shielded by the dark portions of the negative, so it doesn't change. A wash cycle then scrubs away this unhardened polymer, leaving behind a perfect mold in the shape of the stamp. Now they cover the mold with a sheet of synthetic resin called Bakelite and put it into a machine called a vulcanizer. The machine heats the Bakelite to 154 degrees Celsius, then forces it into the mold using 2 to 3 tons of pressure. After 4 minutes, the Bakelite stamp is ready. To be more productive, the factory actually molds several stamps at a time. Next comes the built-in ink. They screw the Bakelite stamps into what's called the pre-ink mold, then pour in a mixture of ink and gel. They cover the mold and vacuum out the air, a process that takes 12 minutes. The mold then goes into a heat press for 17 minutes. The press applies 2 tons of pressure to expel excess ink and heats the ink gel to 127 degrees Celsius, transforming it to roughly the consistency of a marshmallow. So it won't overcook, the mold goes onto a special cooling table for 12 minutes. Next, it's set out to cool for another 45 minutes, this time on newspapers, which soak up more excess ink. Finally, they wrap the mold in paper towels and newspapers and vacuum out the last drops of excess ink. Then they quickly seal the back of the stamp to lock the ink in. Now they can cut apart the individual stamps. They glue the stamps by hand onto the base of the stamp handles. Before they're shipped out to the customer, all the stamps undergo a quality control check to make sure they'll leave a lasting impression. Cranberries are one of just a handful of fruits that are native to North America. Before the Europeans arrived, the Indians used them for food and medicine. The cranberry vine is well suited to a harsher climate. It thrives in low temperatures and loves acidic soil that's scarce in nutrients. Cranberries are ripe for the picking in late September. At harvest time, farmers flood their fields to make the cranberries float to the surface. Then they use a machine called a beater. It generates underwater turbulence, pulling the berries off the vines. The beater is suspended from a mobile bridge that's computer-guided to systematically work its way through the entire field. The beater cuts a swath about 7 meters wide with each sweep. Workers move the floating cranberries to one corner of the field, where a pump transfers them to a waiting truck. Along the way, the berries get a preliminary rinsing to remove branches and leaves. At the factory, the truck unloads its cargo. The cranberries travel along a water canal and onto a conveyor belt, then through a cleaning station, where workers use brushes and water jets to get rid of any remaining leaves and branches. Then they dump the cranberries into large bins to be frozen for up to several months. To produce cranberry juice, they defrost the frozen berries in hot water, then mash them, skin, seeds and all, into a puree. They add special enzymes to break up the pectin molecules, making the puree less viscous and therefore easier to press. The press processes 8 tons of puree at a time. That's the weight of 1.5 elephants. It takes 3 to 4 pressing cycles to extract all the juice. The juice then goes through a sophisticated filtration system. The 216 filters remove any plant particles or bacteria larger than 1 micron. A micron is 1,000 times smaller than a millimeter. Then they evaporate the water until the juice is 10 times more concentrated. Cranberries not destined for juice go through a grading process. Undersized berries drop down through the holes of a giant sifter. The bigger cranberries move on to the grading table, where workers remove any that are substandard. An electronic sorter then scans the remaining cranberries for color, signaling an air gun to blow any reject berries off the production line. The rest move on to the packaging department or continue down the line to be dried. Cranberries destined for drying are automatically seeded, cut in half and pressed, then soaked in a sugar and water solution to make them sweeter. The side-to-side motion of the conveyor belt spreads the berries thinly so that they'll dry evenly. The hot air dryer subjects them to temperatures varying from 30 to 80 degrees Celsius. After about 3 hours, the cranberries come out looking like this. As you sip your cranberry tea, ponder this. Cranberries are a source of potassium and vitamins A and C, and drinking cranberry juice can prevent and treat urinary tract infections. Twisting plant or animal fibers into yarn dates back to ancient times, when people fashioned primitive spindles out of sticks. Around 500 BC, the spinning wheel was born in India. Today's factories have fully automated spinning machines that work on the same principle as a spinning wheel. This is a 2-ply commercial yarn, the kind factories use to weave fabric for making jeans and tops. It's made from large bales of raw cotton. Cotton comes from a plant, so naturally some leaves and stems are mixed in with the cotton fibers. To remove them, the first machine passes over the bales and removes a 5mm layer of cotton, then sends it through a duct system to the blending and cleaning machine. That machine processes 500 kilograms of cotton per hour. The cotton comes out evenly blended and cleaner, but still not clean enough. So it goes into a second cleaning machine, which finishes the job. Now the cotton goes through what's called a carding machine. It has huge rollers with wire teeth. They comb out the tangled fibers and line them up in parallel rows. The machine also discards any fibers that are too short to process. Next stop, the coiler. This device takes the rows of fibers and forms them into a thick and loose first stage yarn called sliver. The slivers move on to the drawing machine. It lines them up 6 at a time and draws them out, stretching them to form a second stage yarn. Then a machine called a roving frame stretches this second stage yarn, strengthening it by thinning it out until it looks like this. This third stage yarn is called roving. Depending on the type of yarn they're making, it's anywhere from 3.5 to 16 times thinner than sliver. They now stretch the roving up to 30 times thinner, which strengthens it even more. The yarn is finally finished. Now they have to transfer the yarn from all these small spools onto huge industrial-sized cones, 20 spools to a cone. One transfer method uses the winding machine. It winds the yarn from the first spool onto the cone. Then it automatically takes the back end of that yarn and attaches it with a knot to the front end of yarn from the next spool. It winds it onto the cone, then attaches the back end to the front end from the next spool, and so on. As each spool empties, the machine automatically discards it. And while all that winding's going on, the machine's optical sensor, that white object you see crossing the screen, does a quality control check. If a portion of yarn doesn't meet specifications, the winding stops, the machine cuts off the offending portion, then reconnects the ends and resumes winding. This is air jet spinning, another method of making yarn from slivers and winding it onto giant spools known as tubes. A suction tube grabs the front end of one spool and connects it to the back end of the previous one, again with a tiny knot. Before fully automated machines like this were invented 50 years ago, all that knotting had to be done by hand. The thin finished yarn is 200 times lighter than the thick first stage yarn that came out of the carding machine. From start to finish, spinning this yarn has taken 48 hours. You might not have noticed, but road signs have undergone a subtle change in recent years thanks to advances in technology. Today's signs are more reflective than ever. You can actually read them in the dead of night, even when the only source of illumination is your car's headlights. The earliest road signs were crude, a stick in the ground or a heap of stones to mark a route. In the Roman Empire, stone posts were erected along roadsides at regular intervals, indicating the distance to Rome. Centuries later, stone marker systems gave way to wooden cross signs pointing in several directions at once. The international system of road signs we know today came out of the first International Road Congress held in 1908. The process of manufacturing a road sign starts with a computer. The government strictly regulates the specifics of the design and requires a certain degree of reflectivity. The computer's specialized software guides a machine to cut the design on a sheet of film. Once the design is cut, workers carefully peel off and discard the pieces. What's left is a film stencil of the sign, in this case, a French stop sign. They inspect it for defects, then prepare a screen of polyester fabric that they'll later use to print the sign. They start by coating it with a thin layer of light-sensitive emulsion. Once the emulsion's dry, they adhere the film stencil, using vacuum pressure to flatten it and get rid of any creases or air bubbles. Then they expose the screen to an intense 6,000-watt light for 7 minutes. This activates the emulsion on the lettering and area outside the octagon, what's not shielded from the light by the film stencil. This exposed emulsion hardens, plugging the minute holes between the screen's fibers. After rinsing, you see the result. Elsewhere in the factory, meanwhile, workers cut the aluminum panels on which the signs will be printed. Using a punch press, they round out the edges and make holes for the bolts that'll later attach the sign to the post. They stamp on the company name and the year of manufacture for warranty purposes. They immerse the panels in a chemical bath to remove grease and other residues. Then they rinse off the panels and dip them in an acid solution that seals the metal to make it better withstand harsh weather. Next, they laminate the aluminum panels with a film containing minuscule glass particles. This film will make the sign reflect in the dark when light hits it. Then they cut the panel to the final shape. Now they can finally print the sign. The process they use is called silk screening, although the fabric screen, as you saw earlier, isn't actually silk, it's polyester. The machine forces the ink down through the screen onto the panel. The ink penetrates through the open fiber holes of the octagon, printing the red background of the stop sign. But it can't penetrate through the blocked fiber holes of the lettering and area outside the octagon, so those remain white. The freshly printed signs pass through a dryer at 66 degrees Celsius for 5 minutes. To produce street signs, workers first laminate aluminum panels with reflective film for the background color. Then either silk screen the street name or apply self-adhesive reflective lettering. But it's back to the silk screening process for printing multicolored signs. Workers print them one color at a time with a drying cycle between colors. All the film stencils are carefully stored for future use. The printed signs go into an oven for a final curing at 176 degrees Celsius, an hour for a one-color sign, a half hour per color for a multicolored sign. The ink is transparent enough not to block the reflective film underneath. Therefore, the entire sign, not just the lettering, is highly reflective. That maximizes the sign's visibility, thereby minimizing the excuses drivers can come up with for not heeding it. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net. The How It's Made crew vehicle is courtesy of Subaru Canada.